There are places in this universe where outward stops meaning anything. Not places where gravity is merely strong, not places where matter is merely dense. Places where the structure of space itself has been bent so far that escape is no longer a matter of speed, courage, or technology. Light can leave a star. It can leave a galaxy. It can cross millions of years of darkness and still arrive here, carrying news from the edge of the observable cosmos. But in a black hole, even light runs out of future. That is the first illusion to give up. A black hole is not a cosmic vacuum cleaner. It is not a hole punched through reality. It is not empty. It is what happens when matter forces the geometry of the universe into a condition from which there is no longer a meaningful way back out. Not because something is grabbing too hard, but because space-time itself has been rearranged. A black hole is what space becomes when leaving is no longer a physical option. And that makes the real question much stranger than it first appears. Most people ask how black holes form. That is the easier question. Massive stars die. Matter collapses. Gravity wins. But that answer only describes the route. It does not explain the destination. It does not explain why the laws of nature permit such a destination at all. Why the universe contains regions where causality narrows, where horizons appear, where information, entropy, geometry, and time begin to knot themselves together so tightly that our clean categories stop holding. Why does the universe need black holes? Not why are they possible. Why are they there at all, waiting at the far end of collapse like a sentence gravity was always trying to finish? Because if black holes are only bizarre astronomical accidents, then they belong at the margins of physics. Interesting, violent, exotic, but still secondary. If they are something else, if they are the natural endpoint of taking gravity seriously, then they are not at the margins at all. They are central. They are what reality does when it is pushed past every gentler compromise. And the universe seems to make them everywhere. At the center of almost every large galaxy, including our own, there is a supermassive black hole. Some weigh millions of suns, some weigh billions. Across the Milky Way, there should also be a vast unseen population of stellar mass black holes, the collapsed remnants of stars that once burned themselves into temporary stability and then lost the argument. These objects are invisible in the ordinary sense. They shine no light of their own, yet they help shape galaxies, redirect gas, power jets, generate gravitational waves, and force some of our deepest theories into conflict. That is another illusion worth breaking early. Black holes are often treated as endings. In one sense, they are. A star can collapse into one. Matter can disappear behind one. Information, at least in the classical picture, can seem to vanish into one. But black holes are also engines, regulators, archives, tests. They sit at the intersection of stellar death, galactic architecture, thermodynamics, and quantum theory. They are not where the story stops. They are where several stories are forced into the same room. To feel why they exist, you have to begin somewhere more familiar than a horizon. You have to begin with a star. A star looks permanent because human time is too small to measure its hesitation. Every star is a negotiation between two enormous facts. Gravity pulls inward with tireless patience. Fusion pushes outward with impossible violence. Deep in a stellar core, atomic nuclei are stripped, slammed together, forced past their mutual repulsion, and rearranged into heavier elements. In that process, a little mass becomes energy, and that energy floods outward as pressure. That pressure is the only reason the star does not immediately collapse under its own weight. So, when we look at a star, what we are really looking at is a successful delay. A star shines by postponing its own verdict. For millions or billions of years, depending on its mass, that delay holds. The balance is imperfect, turbulent, alive with convection and shock and magnetism, but it holds. Gravity keeps trying to compress the core. Fusion keeps answering. The star becomes, in effect, a furnace built out of argument. And because the argument lasts so long, we mistake it for nature's default condition. A star is not what matter prefers to be forever. It is what matter can be for a while when there is still fuel left to burn against collapse. That distinction matters because it changes the emotional center of the story. Black holes are usually framed as dramatic intrusions into an otherwise stable universe. But stability is often just temporary resistance that happens to last longer than a human civilization. The universe does not guarantee enduring forms. It permits them under conditions, remove the condition, and the form goes with it. Inside a massive star, those conditions get harsher with time. Hydrogen fuses into helium, helium into heavier elements. The core contracts, heats, ignites new stages, and presses onward. Each new fuel burns faster. Each new layer is less forgiving. It is a strange hierarchy of brilliance. The more advanced the star becomes, the more desperately it lives. Near the end, the timescales collapse. What took millions of years at one stage may take days at another. The star has not become stronger. It has become cornered. And then it reaches iron. Iron is the quiet betrayal at the center of the story. Up to that point, fusion can return energy. It can keep the pressure flowing. But iron does not pay the same way. Fuse lighter nuclei and you can push back against gravity. Try to keep going past iron in the same spirit, and the economy fails. The core can no longer earn enough outward force to support its own weight. The truce ends. The furnace goes dim at exactly the moment the pressure becomes most necessary. This is where language usually becomes dramatic too quickly, as if gravity suddenly turns cruel. But gravity does not change character. That is what makes it frightening. It does not rage. It does not attack. It simply continues. All that inward demand was always there. Only now, nothing meaningful is answering it. The core collapses, not leisurely, not symbolically, catastrophically. In less than a second, regions larger than worlds can cave inward. Electrons are crushed into protons. Neutrinos burst outward in numbers so absurd they stop sounding physical. The outer layers may rebound in a supernova, bright enough to briefly challenge the light of an entire galaxy. But the center keeps descending, and the deeper point is no longer about explosion. It is about surrender. Matter has lost every softer negotiation it had available. If the remaining core is light enough, another form of resistance may still survive. Compression can pack matter into a neutron star, a city-sized remnant so dense that a spoonful would outweigh mountains. That object is already an insult to ordinary intuition. But even neutron degeneracy, even the quantum pressure created by matter, forced into one of the tightest known arrangements in nature, is not infinitely generous. There is a limit to how much reality will let matter resist itself. Beyond that limit, there is no stable object left to become. No denser star waiting in reserve. No hidden shelf beneath neutron matter. No quieter compromise. Collapse keeps going. And somewhere in that descent, the story stops being merely astrophysical. It becomes structural, because once enough mass is forced into a small enough region, the issue is no longer simply density. The issue is that spacetime itself can no longer preserve the old distinction between inside and outside in the way our intuition expects. The paths that once led away begin to curve back. The future narrows. Escape ceases to be a direction the universe offers. What forms then is not a solid sphere of darkness sitting inside ordinary space like a cannonball in a room. What forms is a horizon, a boundary with a terrifying subtlety. From far away, it looks like a point of no return. But locally, it is stranger than that. It is not a wall you strike. It is a place where the geometry has changed so completely that every physically allowed path ahead leans inward. Nothing has to grab you. The world itself has already closed. This is why black holes feel different from every other object in astronomy. Planets can crush you, stars can incinerate you, neutron stars can tear atoms apart. But all of those still belong, in some sense, to the ordinary vocabulary of things. They are extreme versions of matter arranged in space. A black hole is more severe. It is the moment the arrangement of space becomes the thing that matters most. And once you see that, the opening question deepens. Because if black holes are not just dense corpses, not just violent leftovers, not just spectacular oddities, then their existence says something uncomfortable about the universe itself. It suggests that reality contains conditions under which all familiar forms of resistance fail. And when they fail, the laws do not improvise mercy. They remain consistent. They carry the logic through. Black holes are not where the universe becomes lawless. They are where the law becomes unbearable. And that raises the next pressure point. If a black hole is what appears when every ordinary defense against gravity has been exhausted, then we need to ask a harder question than how stars die. We need to ask why collapse has an endpoint at all. Why the universe does not merely crush matter forever, but produces something as precise, as mathematically sharp, and as conceptually devastating as a horizon. Because a black hole does not begin with darkness. It begins with a failure of negotiation. That is easy to miss because the imagery is so overwhelming. We picture the final state first, the invisible sphere, the event horizon, the impossible gravity, the silent center from which no signal returns. But a black hole only makes sense if we understand what had to be exhausted before reality was willing to build one. It is the last answer, not the first. And like many final answers in physics, it is less theatrical than it is absolute. A star, for most of its life, is not a triumph over gravity. It is a temporary arrangement that gravity allows under pressure. That distinction matters more than it seems. We speak of stars as if they are self-sustaining presences, serene beacons scattered across the dark. But inside every star, equilibrium is expensive. The outward pressure that holds the star up has to be paid for continuously, second after second, by nuclear fusion in the core. The star is not standing on firm ground. It is standing on expenditure. Every second, the sun converts hundreds of millions of tons of hydrogen into helium. A little mass disappears into energy, and that energy pushes back against collapse. Massive stars do the same thing, but faster, hotter, and with less patience. The larger the star, the more furiously it must burn just to remain itself. Size is not security, it is appetite. That is one of the quiet reversals hidden in astrophysics. The most massive stars look the most powerful, but in a deeper sense they are the least stable. Their gravity is stronger, which means the pressure needed to resist that gravity must also be stronger, which means they spend their fuel more wastefully. They live in brilliance because they cannot afford moderation. A small star can endure for tens or even hundreds of billions of years. A very massive one may live only a few million. The greater the radiance, the shorter the reprieve. So, when we ask where black holes come from, the answer is not simply from dead stars. They come from stars that were too massive to end gently. They come from systems whose entire existence was built on a rate of burning that guaranteed an extreme conclusion. Their death is not separate from their life. It is already written into the way they shine. And deep inside those stars, the logic tightens. Hydrogen fuses into helium. When hydrogen runs low in the core, gravity compresses the interior further, raising the temperature until helium can begin fusing into carbon and oxygen. In sufficiently massive stars, the process continues. Carbon into neon, neon into oxygen, oxygen into silicon, silicon into heavier nuclei. Layer after layer, the interior starts to resemble a nested catastrophe. Shells of burning elements stacked around an ever more compressed core, each stage shorter than the last, each one extracting a little more stability from matter before the options run out. This is not just stellar chemistry, it is time becoming more expensive. In the earlier phases, a star can spend millions of years on a single fuel. Near the end, those fuel stages shrink violently. Silicon burning may last mere days. The whole object begins to feel less like a settled body, and more like a structure running through its final reserves at impossible speed. The star is not opening new possibilities. It is using up the last available ones. Then it reaches the point where the central engine can no longer make profit from fusion. Iron is the decisive threshold because iron nuclei sit near the peak of nuclear binding energy. Fusing lighter elements up to iron can release energy. Trying to push significantly beyond that, through ordinary stellar fusion, consumes energy instead of yielding it. And a star does not have the luxury of sentimental continuation. If the core cannot generate enough outward pressure, gravity does not pause to admire what came before. The pressure drops. the inward demand remains. Equilibrium collapses. The star does not explode first. It falls first. That sequence matters because popular descriptions often blur it. The supernova becomes the headline, the visible violence filling the imagination, but the deeper event begins in silence, in the core, when the support fails and matter begins to plunge inward at a speed measured not in images, but in fractions of a second. The collapse is so sudden that the core outruns almost every ordinary intuition we have about objects. Electrons, which normally help provide pressure through their refusal to occupy the same quantum states, are forced into protons. They combine into neutrons, flooding the region with neutrinos. The core contracts from something Earth-sized to something city-sized with terrifying speed. If the remnant core is not too massive, neutron degeneracy pressure can halt the collapse. Then nature gives you a neutron star, one of the strangest objects that still counts, by any human standard, as matter. An object with more mass than the sun, compressed into a sphere perhaps 20 kilometers across. Matter so dense that the distinction between atomic and astronomical begins to feel broken. A place where crust, superfluid interior, magnetic field, and rotation all operate at scales that make ordinary language sound naive. A neutron star is already a rebuke to common sense. It tells us that matter can survive conditions far beyond anything a star, planet, or laboratory can sustain. It tells us that the universe has deeper shelves beneath the visible one. But the existence of neutron stars also teaches a harder lesson. Even this is not the bottom. There is a mass beyond which neutron degeneracy cannot save the core. Quantum mechanics can delay collapse, but not grant infinite amnesty. There is no promise in the laws of nature that matter will always find another state to hide in. There are only specific forms of resistance, each with conditions, each with limits. And once those limits are passed, the collapse no longer has a known material answer. That is the moment the question changes. Up to this point, we can still speak, however strainedly, in the language of stuff, gas, plasma, atomic nuclei, degenerate matter, but when the remnant is too massive and too compact, what kind of matter is it? Stops being the right question. The deeper issue is no longer composition. It is geometry. Mass energy has been driven into such confinement that spacetime itself must respond in a qualitatively new way. This is where the common picture of gravity begins to fail. We inherit a simple intuition early. Gravity is a force that pulls one object toward another. That picture is useful for falling apples, orbiting planets, and spacecraft trajectories. But black holes live beyond the comfort zone of that intuition. In Einstein's general relativity, gravity is not fundamentally a pulling rope. It is the curvature of spacetime, caused by mass and energy. Matter tells spacetime how to curve. Curved spacetime tells matter how to move. Usually that geometry is gentle enough that we can pretend we are dealing with forces in an ordinary arena. Near a black hole, the arena itself becomes the drama. Imagine trying to leave a valley. In ordinary circumstances, walking harder gives you a better chance. Now, imagine a landscape so deformed that every road that counts as forward slopes downward into the same abyss. That is closer to what a horizon means, not a prison wall, not a cosmic hand, a future structure so tilted that all allowed motion carries you inward. This is why the event horizon is one of the most conceptually severe things in all of science. It is not just the surface of a very dense object. It is the boundary beyond which the causal architecture has changed. Outside the horizon, there still exist trajectories that lead away, at least in principle. Inside it, every future-directed path leads deeper inward. Escaping becomes like trying to travel north from beyond the North Pole. The phrase still sounds meaningful. The geometry has already made it obsolete. And yet, nothing locally special has to happen at the horizon itself for a large enough black hole. No invisible wall, no sudden flash, no cosmic sign reading past this point. Reality revoked. That subtlety is part of what makes horizons so unsettling. The universe does not dramatize the threshold for your benefit. It simply alters what futures exist. A black hole, then, is not just a crushed star. It is the place where collapse stops being a problem of pressure and becomes a problem of causality. That is why the endpoint feels so precise. The universe is not merely compacting matter to absurd density. It is redrawing the map of possible escape. The black hole is the geometry of no return. But if that geometry is so exact, so mathematical, so cleanly embedded in the laws of relativity, then another question begins to press forward. Did we discover black holes in the sky first, and then learn the equations? Or were they already waiting for us inside the equations, long before we believed the nature would actually build them? They were waiting in the equations first. That is one of the most revealing facts about black holes, not because it makes them more mysterious, but because it makes them less accidental. Long before anyone watched stars being torn apart at galactic centers, long before radio telescopes traced hot matter spiraling into invisible depths, long before gravitational wave detectors heard two black holes collide and ring the fabric of space-time itself, the possibility was already there, dormant inside general relativity like a conclusion physicists did not yet want to accept. Einstein published the field equations of general relativity in 1915. They were elegant, severe, and unlike anything physics had seen before. Gravity was no longer a force acting across a stage. The stage itself had become dynamic. Matter and energy shaped space-time. Space-time shaped motion. It was one of those rare intellectual events after which reality itself seemed to change character. Space was no longer passive. Time was no longer universal. Geometry had become physical. And almost immediately, something disturbing appeared. In 1916, while serving on the Russian front during the First World War, Karl Schwarzschild found an exact solution to Einstein's equations for the spacetime around a spherical, non-rotating mass. It was an extraordinary achievement, a clean mathematical description extracted from a theory that had barely arrived. But hidden inside that solution was a radius, what we now call the Schwarzschild radius, at which the geometry seemed to become singular. To modernize, this was the first clear mathematical doorway to the black hole. At the time, almost no one wanted to walk through it. That reluctance was not irrational. Physics had good reasons to distrust infinities and apparent singularities. Often they meant the model had been pushed beyond its proper domain, or that the coordinates used to describe the situation had broken down. And in the Schwarzschild case, part of the difficulty really was coordinate-based. The singularity at the event horizon turned out not to be a true physical tear in spacetime, but a feature of the coordinates originally used. With better coordinates, the horizon could be described smoothly. The truly pathological region, at least in the classical solution, was deeper in the central singularity, where curvature becomes unbounded. But that distinction took time to understand. And while the mathematics slowly clarified, human intuition kept resisting. Because the real scandal was not the singularity. The real scandal was the horizon. A singularity could be treated, for a while, as a warning sign, perhaps a clue that general relativity would eventually have to give way to a deeper theory. But a horizon was harder to dismiss, because it was not merely an infinite quantity. It was a global change in causal structure. It said that a sufficiently compact mass would create a region from which no signal could return to the rest of the universe. It said that outside and inside were no longer ordinary spatial descriptions. It said that there could exist domains of reality permanently cut off from causal conversation with everything beyond them. That was not just strange. It was offensive to ordinary physical instinct. So, for decades, the idea lived in a half-state, mathematically permitted, physically doubted. Even Einstein himself was uncomfortable with the most extreme implications of his own theory. Many physicists suspected nature would somehow prevent real collapse from proceeding all the way. Perhaps matter would find some new pressure. Perhaps symmetry assumptions made the solutions unreal. Perhaps some unrecognized instability would intervene. The equations were one thing. Real stars were another. But nature was not interested in our comfort. As the 20th century advanced, theoretical work began closing the exits one by one. Subrahmanyan Chandrasekhar showed that white dwarfs, stars supported by electron degeneracy pressure could only exist below a certain mass. Beyond that, the quantum resistance of electrons would not be enough. There was a limit. Stars heavier than that would have to collapse further. This was not a popular conclusion at first. Arthur Eddington, one of the great astronomers of the era, resisted it sharply. The idea that a star might continue collapsing towards something so extreme felt absurd, almost indecent. But Chandrasekhar's mathematics did not care. Then came neutron stars, themselves astonishing. And yet, they did not solve the deeper problem. They merely moved the wall. There was another mass threshold beyond which even neutron degeneracy would fail. Oppenheimer and Snyder, in 1939, studied gravitational collapse within general relativity and showed that, under idealized conditions, a sufficiently massive star could continue collapsing in a way that produced exactly the kind of trapped region the theory seemed to predict. The phrase black hole did not yet exist in common use, but the structure was there. This is where the story becomes more than a history of acceptance. It becomes evidence of something deeper. Black holes were not invented as dramatic explanations for strange observations. They were the consequence of taking a successful theory seriously when it said something psychologically unwelcome. That matters because it separates black holes from a large class of scientific ideas that begin as speculative patchwork. Black holes did not start life as imaginative excess. They began as an unwanted answer. Nature did not surprise us with black holes. Our own equations did. And that gives them a very different philosophical weight. If a phenomenon is introduced mainly to explain a stubborn anomaly, we are always allowed a little suspicion. Perhaps the model is too flexible. Perhaps the explanation is provisional. But when a theory built for one purpose yields, almost against our wishes, an entirely new kind of object, and later the universe keeps producing evidence that the object is real, then we are looking at something stronger than a convenient idea. We are looking at necessity emerging through mathematics. Still, even that can be misunderstood. It is tempting to hear predicted by equations and imagine a universe trapped inside human symbols, as though black holes exist because mathematics said so. The truth is subtler and more severe. The equations did not create black holes. They exposed what follows if gravity is really geometry and if enough mass energy is compressed into a small enough region. Once those premises are true, horizons are no longer Baroque possibilities. They become natural outcomes. The equations are not commandments, they are disclosures. And the disclosure is hard to soften. Collapse is not merely a local disaster inside a dying star. It is a statement about the structure of space-time itself. That is what the early resistance was really circling around. Accepting black holes meant accepting that the universe allows situations in which geometry becomes so dominant that familiar matter-based thinking is no longer primary. The old physical imagination likes objects with surfaces, interiors, compositions, textures, things you can describe as stuff arranged somewhere. A black hole violates that instinct. Its defining feature is not what it is made of in any ordinary sense, but the causal boundary it imposes. If you know its mass, charge, and spin, classical general relativity tells you almost everything externally relevant. The rich details of what collapsed are hidden. The object becomes, in a sense, simpler as it becomes more extreme. That simplicity is eerie. A star is a riot of plasma, radiation, magnetism, turbulence, chemistry, and evolving structure. A black hole, by contrast, is almost offensively austere. It strips away visible biography. It keeps the gravitational consequences and discards the narrative texture. The universe takes a history of enormous complexity and reduces its external description to a handful of parameters. It is as if collapse does not merely destroy structure. It compresses it beneath a horizon and leaves behind a severe public face. The laws do not become messy at the edge of a black hole. They become brutally economical. And once physicists began to accept that, a more unsettling thought emerged. If black holes are this deeply embedded in general relativity, then they are not curiosities confined to rare stellar deaths. They are built into the grammar of a universe where gravity can act at large scales for long times. Give such a universe enough mass, enough time, enough unevenness, enough collapse, and black holes are not an exception. You have to explain away. They are one of the things the universe is naturally going to write. Which means the real story is no longer just about what happens when a massive star runs out of fuel. It is about what kind of world general relativity describes it all. Because if gravity is truly geometry, and geometry can be driven to this kind of severity, then black holes are not the fringe of the theory. They are one of its clearest declarations. They tell us that under sufficient compression, reality does not invent a softer ending. It does not guarantee a final cushion of matter, or pressure, or visible complexity. It permits a horizon. It permits a one-way region in spacetime. It permits collapse to become a change in the architecture of possible futures. And that is why the next step in the descent matters so much. Once you stop thinking of black holes as astrophysical accidents and start seeing them as lawful endpoints of relativistic gravity, another scale opens up immediately. Because a universe that can produce black holes from dead stars may also be able to build them far earlier, far larger, and far more centrally than our intuition once thought possible. Because that is exactly what the universe seems to have done. If black holes were only the remnants of massive stars, they would already be remarkable. They would still represent a place where collapse outruns every known material, defense, and forces, spacetime into a one-way condition. But the universe did not stop there. It appears to have built black holes on a scale so disproportionate and so early that the old image of them as rare stellar graves starts to look provincial. At the center of our own galaxy sits Sagittarius A star, a supermassive black hole with a mass of about 4 million suns. In the giant galaxy M87, the central black hole is measured in the billions of solar masses. We now have direct horizon-scale imaging of such objects, not just indirect hints from the way stars orbit or gas glows, but actual evidence that these severe regions of spacetime sit at galactic hearts as enduring structures. And that alone changes the emotional geometry of the subject. A stellar mass black hole can still be imagined as a local ending, one star exhausted, one remnant left behind. A supermassive black hole at the center of a galaxy feels different. It does not sit at the edge of the story. It sits in the middle of one of the largest organized structures the universe knows how to make. Suddenly, black holes are not just what happens after brilliance fails. They are part of the architecture around which brilliance itself may organize. That realization has only sharpened in the last few years, because the early universe has turned out to be less patient than we expected. For a long time, there was at least a comforting sequence in our minds. First, the young universe cools, then matter gathers, then stars ignite, then galaxies assemble, then, after enough time and enough mergers, some black holes grow large. The picture was complicated, but emotionally manageable. It allowed scale to mature in stages. It allowed giants to arrive late. But observation keeps disturbing that comfort. The James Webb Space Telescope has found active supermassive black holes astonishingly early, including one in a galaxy just 570 million years after the Big Bang, along with evidence that massive black hole activity and even black hole mergers were already underway when the universe was still in its first fraction of a billion years. That does not mean we understand the full story yet. It means the story became harder. Because once you place a rapidly growing supermassive black hole that early in cosmic history, time itself becomes part of the puzzle. Ordinary stellar remnants can seed black holes. That much is clear. A massive star dies. The core collapses. A black hole forms. But getting from a stellar remnant to a monster, millions or billions of times the mass of the sun, is not trivial. Growth by accretion is limited. Radiation from infalling matter pushes back. Mergers help. But mergers take history. And the early universe did not have much history to spare. So the question shifts again. Not simply, can black holes grow? But how did the universe begin building giants before our comfortable timelines were ready for them? There are several serious possibilities. And this is where intellectual honesty matters. Because the evidence is strong that the problem is real, but the exact root is still under active investigation. Some black holes may indeed have begun as the remnants of the first massive stars. then grown with startling efficiency. Some may have formed through direct collapse, where enormous clouds of primordial gas avoided fragmenting into ordinary stars and instead fell inward on a much larger scale, skipping some of the gentler steps entirely. Some may have benefited from unusually dense environments, repeated mergers, or episodes of near-continuous feeding. The universe may not have used one method only. It may have been opportunistic. But every serious option points in the same unsettling direction. Black holes are not late decorative products of cosmic evolution. They are part of its early grammar. The universe seems to start writing them almost as soon as the conditions allow. That matters because it changes what a black hole is doing in the story of structure. If these objects appear only after galaxies are mature, then they are consequences of large-scale organization. But if they appear alongside the earliest stages of galactic assembly, if they are already active, already accreting, already influencing their surroundings when the universe is still young, then the causal arrow becomes less comfortable. Galaxies do not simply produce black holes and keep them as exotic trophies at the center. The relationship may be reciprocal from the beginning. In some cases, the black hole may be helping determine what kind of galaxy can exist around it at all. And that is where the image of the black hole as pure consumer begins to fail. Because a feeding black hole does not merely swallow, matter spiraling inward forms an accretion disk, heated by friction and compression until it becomes one of the brightest engines in the universe. Before gas crosses the horizon, it can radiate with almost obscene intensity. Magnetic fields can collimate part of that inflowing chaos into jets that blast outward across vast distances. Radiation can heat and disperse surrounding gas. Winds can strip a galaxy of the very material from which new stars would otherwise form. A black hole can be the darkest object in a region and the brightest process in it at the same time. That is not a contradiction. It is one of the clearest examples of why black holes should never be reduced to holes. The horizon itself is dark. The machinery around it can outshine galaxies. This is one of the most severe reversals in astrophysics. The black hole is defined by no escape, but its effects can reach astonishingly far beyond itself. It can regulate the temperature of gas in galaxy clusters. It can interrupt star formation. It can shape the circulation of matter through the central regions of galaxies. Its direct physical size may be small compared with the scale of the host system, but its leverage is enormous. A tiny central region can decide whether a galaxy remains fertile or goes quiet. So, we arrive at a deeper claim, one that would have sounded excessive not long ago, and now feels increasingly difficult to avoid. Galaxies do not merely contain black holes. They negotiate with them, and that phrasing is not just poetic. It reflects something physically real. Astronomers have long found empirical relationships between the masses of central supermassive black holes and properties of their host galaxies, especially the velocity dispersion of stars in the galactic bulge. That correlation does not mean we have solved the whole mechanism, but it strongly suggests coevolution rather than indifference. The black hole and the galaxy are not strangers occupying the same address. Their histories are linked. One grows in conversation with the other. Which means black holes are not just endpoints of collapse. They are participants in order. That is a much stranger role than the popular imagination gives them. We are comfortable imagining black holes as destroyers because destruction is visually easy. A star is torn apart, light disappears, matter crosses a boundary and does not return. But the deeper reality is more difficult and more elegant. Black holes can also function as governors. They keep too much gas from collapsing too quickly into stars. They redirect energy back into the surrounding medium. They may help prevent galaxies from becoming catastrophically over-efficient at turning matter into light. In other words, black holes can limit excess. A universe with gravity has a problem. Gravity gathers, left unchecked. It keeps gathering. It builds stars, clusters, galaxies. But gathering without regulation is not the same as structure. Sometimes the universe seems to require concentrated violence to prevent larger disorder. A black hole at a galactic center can act like exactly that kind of concentration, an extreme object whose local severity helps organize a much broader system. And now the earlier question begins to mature. Why does the universe need black holes? Not because it needs monsters for drama. Because a universe that permits gravity to build structure may also require mechanisms that prevent structure from running away into simpler, more catastrophic forms. Black holes are not gentle, but gentleness is not the same thing as stability. Sometimes stability is purchased through hard constraints. Sometimes coherence is protected by something that looks from up close, like devastation. That is why the subject keeps widening. Every time black holes seem to settle into one role, remnant or monster, destroyer or engine, they unfold into something larger. They are remnants of stellar collapse. They are central engines of quasars. They are regulators of galaxies. They are signs that geometry can dominate matter. They are clues that the deepest laws of the universe are willing to remain consistent even when consistency becomes almost unbearable. And yet the story still has not reached its sharpest edge. Because all of this, stars dying, galaxies growing, jets erupting, quasars blazing across the early universe, still describes black holes as actors within the known order of physics. The next step is harsher. The next step is where black holes stop merely shaping the universe and begin interrogating the laws that shape them. Because up to this point, black holes can still be described as extreme successes of known physics. Violent, yes. Unforgiving, certainly, but still intelligible within a broad, familiar grammar. A massive star exhausts its fuel. Collapse outruns pressure. Relativity shapes the outcome. A horizon forms. Accretion lights the surrounding dark. Galaxies negotiate with the invisible engine at their centers. Severe as all of that is, it still feels like the universe behaving according to established rules. Then black holes begin to do something more disturbing. They stop being merely objects inside our theories and become places where our theories are forced to answer for themselves. That is the true midpoint of the descent. Not when black holes become bigger, not when they become brighter through accretion or more dramatic through mergers. The deeper turn comes when we realize that a black hole is not only a phenomenon to be explained, it is also a test, a pressure chamber, a place where the great frameworks of modern physics are pushed into each other hard enough that their coexistence stops feeling comfortable. General relativity handles gravity magnificently. Quantum theory handles the microscopic world with equal authority. Each has survived experimental assault with astonishing success. Each governs an immense domain of reality. And for much of 20th century physics, that uneasy division was tolerable. Use relativity for stars, galaxies, expansion, geometry, black holes in their large-scale form. Use quantum theory for atoms, fields, particles, radiation, information at the smallest scales. The universe seemed willing to let us work with two profound truths at once, even if we did not yet know how to fuse them completely. Black holes make that arrangement feel temporary. Because a black hole is built by gravity, described by geometry, and yet haunted everywhere by quantum questions. The horizon defines what can escape. The singularity, if classical relativity is taken literally, suggests a breakdown where curvature becomes unbounded. Accretion disks glow through ordinary high-energy astrophysics, but the most unsettling issues gather at the edge of what the horizon means for information, entropy, and the continuity of physical law. Black holes do not merely live in the overlap between our theories. They force the overlap into crisis. To see why, it helps to notice how strange the black hole already is, even before quantum theory enters the room. Ordinary objects have interiors we think we can, at least in principle, describe. A planet has layers, a star has pressure gradients, composition zones, convection, magnetic complexity, even a neutron star, severe as it is, still invites a language of matter under conditions. A black hole resists that instinct. From the outside, classical relativity allows astonishingly little visible detail, mass, spin, charge. Beyond that, the collapsed history is hidden. The rich biography of whatever formed the black hole seems to vanish from public view. This is sometimes summarized by the phrase, "black holes have no hair," which sounds casual for something so conceptually severe. The point is not that black holes literally lack texture. The point is that their external description is radically compressed. Enormous physical complexity can collapse behind a horizon and leave, to outside observers, a startling simplicity. That alone feels like a warning. Because physics is usually generous with information. Scatter light off an atom and you can infer energy levels. Study a star's spectrum and you can recover composition, temperature, motion, magnetic effects. Watch a planet wobble and you can infer an unseen companion. Reality often hides things, but it also leaks. It leaves signatures. It allows reconstruction. A black hole seems to break that generosity. It permits the world to become externally simple, while internally withholding almost everything that led there. And yet quantum theory has trained us to distrust any story in which information simply disappears from the universe. That principle is deeper than it first sounds. In ordinary speech, information means messages, data, encoded symbols. In fundamental physics, it means something more severe, the complete specification of a system's physical state. Quantum mechanics is built so that this information, however scrambled, is not destroyed by lawful evolution. It can become impossible to recover in practice. It can disperse into forms no human could ever reconstruct. But at the level of principle, the evolution is unitary. The total information is preserved. A book can burn. The words vanish from readability. The pages become heat, gases, ash, light, chemical debris. For practical purposes, the message is lost forever. But in the quantum description, the detailed state of all those outgoing fragments still encodes what happened. The order is ruined. The recovery is hopeless. Yet the underlying evolution does not simply erase the past. This is one of the cold triumphs of physics. Apparent loss is often only dispersion beyond mercy. So, now place that principle beside a black hole. Matter falls inward. It may be a gas cloud, a star, a magnetic plasma, a stream of particles carrying an immense amount of detailed structure. From the outside, all of that rich information seems to cross the horizon and become inaccessible. Classically, the black hole settles down into a simple exterior state characterized by very few parameters. If black holes were perfectly eternal, we might try to hide the problem behind the horizon indefinitely. The information would not be destroyed. It would merely be unreachable. But black holes are not perfectly eternal. That sentence changed the entire subject. In the early 1970s, Jacob Bekenstein proposed something audacious. Black holes should have entropy, not metaphorically, not as a loose analogy, as real thermodynamic objects. The idea emerged from a deep tension. The area of an event horizon seemed to behave a little like entropy in the laws of the black hole mechanics. If you dropped entropy-bearing matter into a black hole, the horizon area increased. Perhaps this was not an accident of symbolism. Perhaps black holes truly possessed an entropy proportional to the area of their horizons. Stephen Hawking initially resisted that suggestion, and he had a strong reason. If black holes have entropy, then by the logic of thermodynamics they should also have temperature, and if they have temperature, they should radiate. But classically, black holes do not radiate, they only absorb. Then Hawking did the quantum field theory and curved spacetime, and the answer was worse than the objection. Black holes are not perfectly black. When quantum effects near the horizon are taken seriously, a black hole emits thermal radiation, not because particles crawl out from inside the horizon in the naive popular sense, but because the quantum vacuum in curved spacetime does not remain as inert as classical intuition would like. To distant observers, the black hole behaves as a thermal object, with a temperature inversely related to its mass. Large black holes are colder. Small black holes are hotter. Given enough time, a black hole can evaporate. That result did not merely add a detail, it detonated the old arrangement. Because now the black hole is no longer an eternal vault. Matter falls in carrying detailed information. The black hole radiates outward in a thermal spectrum that, at least in Hawking's original treatment, appears to carry no memory of the specifics. Then the black hole shrinks. If evaporation completes, what remains? A bath of thermal radiation, a dead end of detail. The rich microphysical distinctions of what fell in appear to have been washed into featureless heat. And if that is really what happens, then quantum theory's deepest rule has been violated. This is the black hole information paradox, and its force is easy to underestimate if it is presented too casually. It is not just a puzzle about bookkeeping, it is a collision over whether reality is allowed to forget. A black hole is terrifying to physics for the same reason amnesia is terrifying to a mind. Not because memory is sentimental, but because continuity depends on it. If information can truly be destroyed, then the quantum world is not evolving the way we thought. If it cannot be destroyed, then Hawking's original semi-classical picture is incomplete in a way that must become visible, somehow, in or around the horizon. Either the radiation is not perfectly thermal in the full theory, or the horizon is not as smooth as classical relativity suggests, or information escapes in a way we do not yet understand, or some more radical restructuring of spacetime and quantum law is required. Notice how the role of the black hole has changed. It is no longer just the endpoint of stellar collapse, no longer just the engine of quasars, no longer just the governor of galaxies. It has become a question the universe is asking itself. Can geometry hide information without destroying it? Can thermodynamics, relativity, and quantum mechanics all remain true at once? Can the horizon preserve the smoothness relativity demands and still return the detail quantum theory forbids us to lose? The subject has crossed a boundary of its own. We are no longer merely observing black holes. We are using them to interrogate the internal coherence of physics. And that is why black holes matter far beyond astronomy. A comet can be spectacular. A supernova can be transformative. A pulsar can be exotic. But none of those objects strikes as directly at the architecture of explanation itself. Black holes do. They sit exactly where the lawful collapse, space-time geometry, thermodynamic accounting, and quantum information can no longer remain politely separated. They force us to ask whether the universe is truly built out of the categories we have been using, or whether those categories only survive because we have not driven them hard enough. The disturbing possibility is not that black holes are exceptions. The disturbing possibility is that they are exposures, places where the hidden terms of reality come into view because every softer condition has already been stripped away. And once that happens, the horizon begins to look different again. Not merely as a point of no return, not merely as a causal boundary, but as a thermodynamic surface, a place where area, entropy, temperature, and information begin to gather with impossible density, which means the next descent is no longer about what falls into a black hole. It is about what the horizon itself may be forced to remember. Because once entropy arrives at the horizon, the black hole stops looking like a grave and starts looking like an accounting system. That is one of the most difficult shifts in the entire story, because it forces us to abandon another deeply rooted instinct. We like to imagine entropy as something diffuse, steam escaping a kettle, smoke spreading through air, heat bleeding into a room, order dissolving into messy abundance. Entropy feels volumetric. It feels like something that belongs to interiors, to countless hidden motions inside matter. You expect more entropy to mean more internal complexity filling more space. Black holes violate that expectation with almost insulting elegance. The entropy of a black hole does not scale with its volume in the ordinary way. It scales with the area of its horizon. That single fact lands with quiet violence. Because if taken seriously, it suggests that the deepest bookkeeping in nature may not care about volume as much as we thought. It suggests that the amount of information that can be physically associated with a region of space is somehow tied to the area of its boundary. Not the room itself, but the walls, not the bulk, but the skin. The black hole does not merely bend our intuition about gravity, it bends our intuition about where reality keeps its record. And the numbers are grotesque in the most instructive way. The entropy associated with a black hole is enormous, vastly greater than that of an ordinary star of comparable mass. Collapse does not seem to reduce thermodynamic significance. It amplifies it. A star may have immense complexity, but when it becomes a black hole, the horizon area behaves as though an even more profound count of hidden microstates has come into play. The object becomes externally simpler, while thermodynamically more immense. That reversal is worth lingering on. Usually, Simplicity and reduced informational richness seem to go together. Strip away details, erase distinctions, compress description. You expect the entropy story to become poorer, not richer, but a black hole does something harsher. It presents radical external simplicity while implying unimaginable microscopic accounting beneath or at the horizon. The public face becomes austere. The hidden bookkeeping becomes colossal. It is as if reality has not lost interest in the details. It has moved them somewhere we no longer know how to picture. This is why the horizon becomes so important. Earlier, it was a causal boundary, the edge beyond which outward escape stops existing as a physical future. Then, with Hawking radiation and the information paradox, it became a theoretical crisis point, the place where quantum mechanics and relativity begin to make incompatible demands. Now, it deepens again. The horizon starts to resemble a thermodynamic ledger, a surface that somehow knows how much has been hidden, compressed, or absorbed, even if it will not tell us in any ordinary language. And this is the moment where black holes stop being merely difficult objects and begin acting like clues. Because if the entropy of a black hole scales with area, then one of two things is true. Either this is a bizarre exception, a strange mathematical quirk limited to horizons, and useful mainly inside a narrow corner of gravitational physics, or it is a window into something much more general, that the universe may be more fundamentally organized by surfaces, limits, and boundaries than by the comfortable interior pictures our senses evolved to trust. Physics has spent decades taking the second possibility seriously. Out of that seriousness emerged one of the strangest and most powerful ideas in modern theoretical thought, the holographic principle. The phrase can sound glamorous in a way that invites misunderstanding, as though the universe were literally a projected illusion in some cheap science fiction sense. That is not the point. The deeper suggestion is more disciplined and far more disturbing. It is that the full physical description of a region might, under the right conditions, be encoded on a lower dimensional boundary. The apparent volume may not be where the deepest description fundamentally lives. A black hole did not prove that in any universal, final sense, but it made the thought difficult to dismiss, because the horizon kept insisting on area. And when nature insists on something that conceptually severe, good physics pays attention. Notice how far the subject has now moved from the popular image of black holes as giant cosmic drains. We are no longer asking what happens if you fall in. We are no longer even primarily asking what black holes do to nearby stars or gas. We are asking whether the deepest architecture of physical description is more economical, more boundary-driven, and more alien to common sense than we ever wanted it to be. That is why black holes exert such power over thought. Not because they are dark, not because they are dangerous, but because they repeatedly expose the possibility that our ordinary categories are provincial. We think in terms of objects occupying volume, histories unfolding inside containers, matter distributed through space. Then the horizon appears and quietly suggests that the container may not be the deepest part of the story at all. The boundary may be where reality keeps score. That line sounds philosophical until you remember that it was forced on us by thermodynamics. And thermodynamics is not sentimental. It is one of the hardest, most unforgiving descriptive frameworks in all of science. It counts what can happen. It measures irreversibility. It places price tags on order. When thermodynamics starts pointing toward horizons, we are no longer drifting through metaphor. We are being dragged toward a more severe ontology by one of the coldest disciplines in physics. Still, the situation remains unstable. Because even if the horizon carries entropy, even if it behaves like a thermodynamic surface, even if some deeper theory eventually explains how information is encoded there, we are still left with a brutal question. How can anything that falls inward ever be reflected in outward reality strongly enough to preserve quantum consistency? Hawking's original radiation was thermal. Too thermal, it seemed, to carry the required detail. The paradox did not vanish just because entropy gained an area law. It sharpened. Now, the surface had to matter not only statistically, but informationally. And that demand has driven decades of extraordinary work. Different approaches have tried to answer it from different angles. Some suggest the information is subtly encoded in correlations within the Hawking radiation, invisible in coarse approximations, but present in the full quantum description. Some approaches use holography more directly, treating gravitational systems as dual to non-gravitational quantum theories on a boundary where unitarity is manifest. Some proposals push the drama toward the horizon itself, questioning whether the smooth crossing predicted by classical relativity survives in the exact theory. Others attempt to preserve the horizon's local gentleness while relocating the resolution into subtler global structures. None of this is settled in a fully final sense. That uncertainty matters. The honest story is not that physicists solved the black hole information and paradox neatly and moved on. The honest story is that black holes became one of the places where progress in fundamental physics has been both most profound and most incomplete. They have generated deep insights into entropy, quantum gravity, geometry, and information. They have also refused to yield a universally agreed final picture that can be written down with the same calm closure as a solved textbook problem. That refusal is part of their significance. A black hole is what happens when the universe remains lawful beyond the point where our current formulations remain mutually comfortable. So, the horizon becomes almost unbearable in its conceptual density. It is a causal boundary, a thermodynamic surface, a possible information-bearing structure, a locus where quantum fields produce radiation, a region that may, depending on the full theory, preserve much more of the past than the classical exterior lets on. It is almost too much meaning for one boundary to carry. And yet the universe seems content to place such boundaries at the centers of galaxies. That is another reason black holes feel so disproportionate. They are not rare curiosities hidden in inaccessible corners of nature. The same class of object that threatens our deepest assumptions about information and entropy is also helping regulate structure on cosmic scales. The same phenomenon that generates one of the hardest theoretical crises in physics is also a routine ingredient in galactic evolution. The universe did not isolate the paradox in some sterile thought experiment. It embedded it in reality, which means the next step cannot remain abstract for long. Because black holes are not only thermodynamic ledgers, many of them rotate. And rotation changes everything. A non-rotating black hole is already conceptually severe, but in a certain mathematical sense, it is austere, almost minimal, adds spin, and the geometry becomes richer, stranger, and more active. The black hole no longer merely sits as a perfect one-way sink in space-time. It begins to drag the surrounding geometry with it. The darkness acquires machinery. Space itself is pulled into motion. And then the story changes yet again. Because once a black hole spins, it stops looking like a final tomb and starts looking like one of the most efficient engines in the universe. The horizon keeps its silence, but the space-time around it begins to work. Because a rotating black hole does not merely sit inside space-time. It drags it. That sounds at first like a metaphor designed to make geometry feel vivid. It is not. In general relativity, a spinning mass can genuinely twist the local structure of space-time around itself. Usually that effect is tiny. Around Earth, it is measurable only with exquisite care. Around a rotating black hole, it becomes one of the defining features of the environment. The space near it is not just curved, it is compelled into motion. This is where the image of the black hole as a passive abyss finally breaks for good. A non-rotating black hole is already difficult enough for intuition. It gives you a horizon, a one-way causal boundary, and the severe simplicity of an object whose exterior can be described by very few parameters. But rotation adds a symmetry, activity, and a new kind of violence. The black hole becomes a structure that does not simply swallow. It reshapes the kinematics of everything around it. Even the idea of standing still near it stops making sense. That loss of stillness has a nameable region attached to it, the ergosphere. Outside the event horizon of a rotating black hole lies a domain where the dragging of space-time becomes so intense that no observer can remain stationary with respect to distant stars. You can still, in principle, escape from the ergosphere if you have the right trajectory. It is not the horizon. It is not yet the place of no return, but it is already a place where the geometry has begun to overrule common motion. Space itself is being swept around the hole's rotation, and anything inside that region must participate. The distinction matters, because the ergosphere means that rotation is not just an internal property hidden behind the horizon. It reaches outward. It alters the accessible exterior. It turns the black hole into something more than a final state. It turns it into a machine. And once a black hole becomes a machine, a new question appears immediately. Can you extract energy from it? Remarkably, according to general relativity, the answer is yes. This is one of the strangest and most beautiful consequences of the Kerr solution. The mathematical description of a rotating black hole. Roger Penrose realized that, in the ergosphere, the peculiar structure of spacetime allows processes in which part of an infalling object can end up on a trajectory with effectively negative energy relative to infinity, while another part escapes carrying away more energy than the original incoming object had. The bookkeeping works because the black hole loses a little of its rotational energy in the process. You do not violate conservation. You use the geometry against itself. The idea is austere, almost surgical. A rotating black hole stores energy not as a visible spinning surface, but as angular momentum embedded in spacetime. Under the right circumstances, some of that rotational wealth can be mined. This is not easy in practice, and the Penrose process in its original idealized form is not necessarily the main astrophysical route by which energy is extracted. But the deeper point survives every technical refinement. Black hole rotation is not dead inertia. It is usable structure. A spinning black hole does not just bend space. It drags the meaning of stillness with it. And from that dragged geometry, the most luminous large-scale phenomena in the universe may draw part of their power. Around many black holes, especially supermassive ones feeding at galactic centers, matter does not simply fall straight in. It forms an accretion disk, a flattened, incandescent torrent of gas and plasma orbiting at extraordinary speed, heated by friction, compression, turbulence, and magnetic reconnection until it radiates across the electromagnetic spectrum. Before any of that matter reaches the horizon, it can become ferociously bright. In active galactic nuclei and quasars, the region around the black hole can outshine the entire galaxy that hosts it. But in the most dramatic systems, the disk is only part of the spectacle. From near the poles of the black hole, tightly collimated jets can erupt and extend for thousands, even millions of light years. These are not loose sprays of debris. They are disciplined beams, accelerated to relativistic speeds, punching through interstellar and even intergalactic space. Their power can influence the temperature of cluster gas, suppress star formation, carve cavities in surrounding media, and reshape environments vastly larger than the central engine itself. How does darkness launch structures like that? Not from the inside of the horizon. That popular image is too crude. The physics happens outside, in the tortured region where magnetic fields, inflowing plasma, relativistic motion, and rotational energy interact. One leading mechanism, the Blandford's-Najek process, describes how magnetic fields threading the region around a spinning black hole can tap its rotational energy and help power jets. The exact details depend on plasma conditions, field geometry, accretion state, and simulation-informed magnetohydrodynamics. But the conceptual point is clear. The hole's spin matters. The geometry matters. The black hole is not merely a destination for infalling matter. It is part of an engine that can redistribute enormous energy outward. This is another reversal worth feeling in the body. The object defined by no escape may help drive some of the most far-reaching acts of astrophysical influence in the known universe. That is not contradiction, it is leverage. A black hole concentrates gravity so completely that the surrounding conditions become capable of extraordinary efficiency. Matter falling toward the horizon can convert a large fraction of its rest mass into radiation, often far more efficiently than nuclear fusion in stars. Rotation enriches that efficiency further. The result is that one of the darkest structures in reality can become the center of one of the brightest processes reality permits. And now the old moral picture of black holes really collapses. They are not merely destroyers, not merely endpoints. not merely cosmic trash compactors. They are converters. They translate gravitational depth into radiative violence, rotational structure into jets, local extremity into large-scale consequence. That is why galaxies do not merely suffer their central black holes. They evolve with them. A spinning supermassive black hole coupled to an accretion flow can heat gas that would otherwise cool and condense into stars. It can starve a galaxy of future brilliance precisely by becoming, for a time, too brilliant itself. It can keep a system from collapsing into simpler excess. Again, the same pattern returns, but at a higher register. Black holes limit runaway accumulation by imposing severe local order. A universe with gravity has a chronic tendency to gather matter into ever denser concentrations. Stars are one answer to that tendency. Galaxies are another. But left wholly unchecked, accumulation is not the same as sustainable structure. Too much cooling, too much collapse, too much efficient star formation, and a galaxy burns through its possibilities too quickly. Feedback matters. Regulation matters. The universe seems to use extreme objects to prevent larger forms from becoming less stable. That does not mean black holes are benevolent. Nature is not moral at that scale. A jet that regulates a galaxy can also sterilize a region, blast through gas, and inhibit future generations of stars. The point is not kindness. The point is control. Structure in the universe often survives because energies are redistributed harshly, not gently. And that is why spinning black holes are so revealing. They show that black holes are not only what reality builds when matter loses every negotiation, they are also what reality uses once that severe endpoint exists. Collapse produces them. Rotation operationalizes them. The universe turns a final state into an instrument. It is hard to think of another class of object that behaves with this much conceptual density. A black hole is at once a causal boundary, a thermodynamic puzzle, a possible information ledger, a remnant of collapse, a galactic regulator, and, when it spins, a relativistic engine. Each description is accurate. None of them feels sufficient on its own. That multiplicity is not a sign of confusion. It is a sign that the black hole sits close to a junction point in reality, where categories we normally separate become inseparable. Geometry becomes energetics. Infall becomes luminosity. Darkness becomes influence. Finality becomes machinery. And still, even this is not the end of the pressure. Because the more active a black hole becomes in our understanding, the less satisfying it is to imagine it as eternal. We have already seen why that comfort fails in quantum theory. Hawking radiation means even black holes can evaporate. But the thought changes, meaning after all this. Earlier, evaporation seemed like an abstract correction to the idea of a perfect absorber. Now it becomes something colder. It means that even these immense engines, these regulators, these objects that look like the hardest final statements in astrophysics, belong to time. Even the most absolute structures the universe builds are not monuments. They are phases. And once you let that sink in, a different kind of silence opens. Not the silence of the horizon, the silence of the far future, when the galaxies have dimmed, the fuel is spent, the great engines have gone quiet, and even black holes begin, with impossible slowness, to disappear. And that is when the scale of black holes changes one last time. Up close, they feel violent. In a galaxy, they feel architectural. In fundamental physics, they feel like interrogators. But in the far future, black holes become something else again. The last great reservoirs of structure in a universe that has spent almost everything easier to spend. Human intuition is almost useless here, because every time scale that shaped our minds is too small by absurd degrees. Civilizations rise and vanish in instants compared with stellar lifetimes. Stars themselves are brief compared with the long cooling of galaxies. Galaxies are brief compared with the eras over which the largest black holes can endure. When we call a black hole eternal, what we usually mean is only that it outlasts anything we naturally know how to imagine. Physics is less sentimental. If Hawking's insight is right, and every serious modern discussion of black holes takes that quantum result as foundational, even if the deepest information resolution remains debated, then black holes are not permanent. They have temperatures, they radiate, they lose mass. The rate is almost laughably small for large astrophysical black holes. A stellar mass black hole is colder than the cosmic microwave background today, so in the current universe it absorbs more from its environment than it emits. Supermassive black holes are colder still. Their evaporation times are so vast that ordinary language becomes decorative long before it becomes useful. But vast is not the same as infinite. That distinction is one of the quiet disciplines of cosmology. The universe repeatedly confronts us with durations so extreme that the emotional reflex is to collapse them into forever. Yet forever is a metaphysical word. Physics keeps its own books. If there is a non-zero temperature, there is radiation. If there is radiation, there is mass loss. If there is mass loss, then given sufficient time, even the darkest and most severe objects in existence belong to change. A black hole is long-lived because reality is patient, not because reality grants exceptions. And that matters more than it first appears. Because by the time the far future becomes a black hole universe, almost everything softer has already faded. The stars that burn efficiently burn out. New star formation dwindles as usable gas is consumed, heated, dispersed, or locked away. Stellar remnants accumulate. White dwarfs cool. Neutron stars cool. Planets freeze, collide, are ejected, or remain as dark debris around dying systems. Galaxies, if they remain gravitationally organized on local scales, drift through a cosmos whose large-scale expansion increasingly isolates them from one another. The bright universe gives way to a quieter one, then a quieter one still. In that long thinning, black holes inherit significance almost by elimination. They are what remains when easier forms of stored order have been spent. This is another reversal in the story. Earlier, black holes looked like the negation of structure, places where stars were destroyed, matter disappeared, light failed, and familiar forms ended. But over cosmological timescales, they begin to look almost conservative, not in the moral sense, in the thermodynamic one. They hold on, they persist. They become the last major bound concentrations of mass and the last places where certain forms of extreme gravitational organization still exist. After the age of stars, after the age of active galaxies, after the age of easy light, black holes remain like slow punctuation marks in an increasingly dilute sentence. There is something severe about that image, because it strips the glamour from them without making them less powerful. No blazing accretion disks, no jets carving through cluster gas, no quasars outshining galaxies, just cold, patient horizons in a universe that has gone thin. But patience is not stasis. Hawking radiation means the horizon itself is not a timeless possession. Quantum fields near that boundary force a subtle leakage into being. The picture is often simplified into particle pairs, one escaping and one falling inward. That can be a useful first intuition, but the more responsible statement is colder and cleaner. The vacuum state of quantum fields depends on space-time geometry, and around a horizon, the result is that distant observers describe a thermal flux. The black hole behaves as an emitter, not violently at first, not in any way that matters to present-day astrophysical life, but in principle, unavoidably, it emits. And the smaller it becomes, the hotter it gets. That detail gives evaporation its final cruelty. Large black holes die almost not at all. Small black holes, once they are small enough, lose mass faster. The process accelerates. What was once an almost frozen act of leakage becomes a terminal rush. If black holes are allowed to evaporate completely in the full theory, then the far future of each one is not endless fading, but an eventual, violent final stage, a last outpouring from an object that spent unimaginable ages appearing almost immortal. Even black holes are not monuments. They are long sentences with an ending. That line matters because it changes the philosophical weight of everything that came before. If black holes were perfectly eternal, they could be imagined as permanent loopholes in time, regions where collapse had written a final exception into the cosmos and then simply stopped. But evaporation forbids that comfort. A black hole is not the universe stepping outside history. It is the universe entering a more austere kind of history, one in which even the hardest structures are temporary phases of lawful transformation. That is more unsettling than immortality. Immortality at least gives intuition something stable to cling to, a final object, a permanent abyss, an end state that stays ended. Hawking evaporation takes even that away. It says the black hole is not ultimate matter, not eternal prison, not final archive beyond change. It is a thermodynamic object moving, however slowly, through time like everything else, extreme, yes, severe beyond comparison, but still implicated in process. And this is where the information problem returns with colder force than before. Because if black holes evaporate, then the demand for consistency sharpens mercilessly. Information cannot simply remain hidden behind a horizon forever, if the horizon itself is going away. Whatever reality means by preserving the detailed physical state of what fell in, that meaning must survive not just collapse and horizon formation, but the eventual disappearance of the black hole as a macroscopic object. The far future is not merely a poetic backdrop, it is part of the theoretical pressure. The universe cannot postpone the accounting indefinitely if the ledger itself is evaporating. That is why black holes belong simultaneously to astrophysics and to the foundations of physics. Their birth matters, their feeding matters, their rotation matters, their role in galaxies matters, but their death matters too, because it is in the death of a black hole that the universe loses the excuse of delay. If there is a consistent answer to how information, geometry, and quantum law fit together, black hole evaporation is where that answer must eventually cash out. A black hole does not merely challenge theory by existing. It challenges theory by ending, and when you widen the frame far enough, that ending changes the emotional meaning of the entire cosmos. We tend to imagine the universe as most dramatic in youth, hot beginnings, violent star birth, frequent mergers, brilliant quasars, rampant structure formation. But there is another kind of drama in the deep future, a quieter one in which the great fact is not violence but attrition, not eruption, but the disciplined removal of everything temporary until only the hardest residues remain. Black holes belong to that age not as invaders from elsewhere, but as survivors of every earlier compromise. Then even they are spent. What remains after that depends on assumptions about the ultimate contents and laws of the universe. And honesty matters here. Some aspects of very deep future cosmology rest on extrapolating known physics into domains no observation can directly test in anything like a human timescale. Proton decay, vacuum stability, dark energy behavior, quantum gravitational end states. These are not all settled with equal confidence, but within the standard Hawking evaporation picture, black holes do not escape the broad thermodynamic direction. They are among the last major actors, not actors exempt from the curtain. That restraint is important. The goal is not to replace one myth with another. It is to see the black hole clearly enough that even its disappearance becomes part of the same lawful story. And once you do that, something surprising happens to the original question. Why does the universe need black holes? The answer is no longer exhausted by stellar collapse, or by galactic regulation, or by the information paradox, or by the thermodynamics of horizons. It begins to gather all of those roles into one larger shape. Black holes are what the universe builds when gravity is followed to its honest endpoint. They are how the cosmos stores extremity without abandoning law. They are how structure is sometimes regulated by concentrated violence. They are where entropy, geometry, and information are forced into direct relation. And in the far future, they are the last severe expressions of organization before even that severity is radiated away. Which means the final step is not to ask what black holes destroy. It is to ask what reality would lose without them. What kind of universe would remain if gravity could gather matter, if stars could die, if galaxies could grow, if entropy had to be counted, if information had to be preserved, and yet no horizons ever formed? At that point, the question is no longer about an object. It is about whether a lawful universe could stay coherent while refusing one of its own hardest consequences. Because if you remove black holes from the universe, you do not simply remove a class of exotic objects. You remove a solution. That is the deeper pressure hidden inside the question. By now, black holes have already played many roles. They emerged from stellar collapse when matter lost every softer negotiation. They appeared in Einstein's equations before we believed nature would use them. They grew into supermassive structures early enough to disturb our timelines for cosmic assembly. They regulated galaxies through accretion, radiation, and jets. They turned into thermodynamic surfaces, information crises, and rotating engines. They even followed time into the far future, surviving almost everything easier to erase and then slowly evaporating under quantum law. But all of that still leaves one final possibility to confront. What if black holes had never existed at all? Not what if we never discovered them. Not what if they were rarer. Not what if some observations were misread. What if a universe could have gravity, collapse, stars, galaxies, entropy, quantum fields, and causality, and still refuse to produce horizons? At first, that sounds like a cleaner universe, a more merciful one. A universe where matter can become dense without vanishing behind a one-way boundary, where collapse always finds another stable shelf, another softer form, another way of avoiding this severe geometry, a universe with all the richness of structure and none of the black hole abyss. But the longer you hold that thought against the logic of physics, the less comforting it becomes. Because if gravity is real in the relativistic sense, not just a force, but geometry responding to mass energy, then a universe without black holes would have to prevent certain consequences not occasionally, but fundamentally. It would need a principle that steps in before causal structure can become trapped. It would need matter to discover new forms of resistance every time collapse deepens. It would need nature to keep inventing cushions exactly where the equations, left to themselves, keep converging on horizons. And that starts to sound less like a cleaner universe and more like an evasive one. The black hole is terrible, yes, but it is terrible in a very specific way. It is what happens when the universe refuses to soften its own laws just because their honest consequences become psychologically intolerable. That is why black holes feel so disproportionate. They are not just violent. Supernovae are violent. Gamma-ray bursts are violent. Neutron stars are violent in the pressure they embody. Black holes are something worse for the mind. They are the point at which consistency becomes visible as severity. They are what happens when collapse is not interrupted by preference. If there were no black holes, we would be forced to ask what takes their place. Suppose a massive star exhausts its fuel, the core collapses, degeneracy pressure fails, and still no horizon forms. Then what? Does matter compress forever without changing the causal structure around it? That is not a neutral answer. It would imply a universe willing to tolerate ever more extreme concentration without allowing the relativistic endpoint that concentration seems to demand. Does some unknown pressure always arise at the last moment? If so, from where and under what law? And why with such perfect timing? Does collapse reverse itself? Does matter fragment into something even stranger than anything we have inferred? Perhaps. Physics does leave room for unknowns. But notice the standard of proof here. You would need more than mystery. You would need a replacement for one of the clearest large-scale consequences general relativity appears to allow. And the replacement would have to do real work. It would have to explain why galaxies still regulate themselves, why early compact engines still blaze across the young cosmos, why spacetime still rings in the waveforms we detect from mergers, why horizons keep emerging in the mathematics of gravity, why entropy keeps pointing toward area, why quantum theory keeps finding its sharpest crisis at precisely the place a black hole would be. A black hole is not just another thing in the inventory of the cosmos. It is the meeting point of several demands that would otherwise remain unresolved. This is why the phrase "the universe needs them" can be made rigorous, if handled carefully. Not in the sense that nature has intentions, not in the childish sense that the cosmos wanted monsters for dramatic effect, but in the harder sense that a universe governed by certain laws may require certain structures if those laws are to remain mutually honest under extreme conditions. Gravity needs an endpoint to unconstrained collapse. Causality needs a boundary once escape ceases to be physically available. Thermodynamics needs a bookkeeping scheme when immense entropy-bearing matter disappears from ordinary access. Quantum theory needs some resolution for information when horizons form and evaporate. Galactic structure appears to need extreme compact engines to regulate cooling and star formation at scale. Black holes are where those pressures converge. That does not mean every detail is solved. It means the burden of explanation no longer lies only on the black hole. It also lies on any imagined universe that tries to do without one. And now a subtler point begins to emerge. The universe does not merely need black holes because gravity collapses matter. It may need them because without horizons, there would be no clean way to preserve distinction between what is still causally negotiable and what is no longer recoverable by ordinary means. The horizon is brutal, but it is also precise. It says, beyond this boundary, all future directed paths go inward, no ambiguity, no half permission, no gradual blur where escape is maybe allowed, if the circumstances are poetic enough. Black holes are harsh, partly because they are exact. That exactness matters more than comfort. Nature often appears kind only when we are far from its limits. At the limits, kindness is not what keeps the universe coherent. Boundaries do, conservation does, causal structure does, thermodynamic accounting does. The black hole is one of the places where those disciplines stop being abstract principles and become the architecture of an actual object. Or perhaps object is already too soft a word. A black hole is a verdict reality reaches. And once you see it that way, a great deal of the fear around black holes begins to change character. They remain frightening, but not because they are unnatural intrusions into a sane cosmos. They are frightening because they are natural, because they show what the laws are willing to become when no easier outcome remains, because they expose a universe more committed to internal consistency than to human intuition. There is a severe kind of beauty in that. Not warm beauty, not sentimental wonder, something colder, the beauty of finding that the world does not avert its gaze from its own hardest implications, the beauty of discovering that the abyss is not a loophole in nature, but one of the forms lawful nature is prepared to take. That is why black holes feel philosophically larger than almost any other entity in astrophysics. A planet can be magnificent, a star can be sublime, a galaxy can be overwhelming, but all of them still seem, in some way, to belong to the visible order of things. A black hole belongs to the hidden order beneath visibility. It tells us that what matters most is not always what shines, but what constrains, not what appears rich to perception, but what remains true when perception fails. And that, at last, returns us to the opening wound in a more mature form. There are places in this universe where outward stops meaning anything. At first, that sounded like a terrifying fact about motion. Then it became a statement about collapse, then a statement about geometry, then about entropy, then about information, then about the far future. Now it becomes a statement about reality itself. Because the existence of a black hole means the universe contains conditions under which all familiar resistance runs out. And when it runs out, the laws do not fracture into mercy. They close into form, they produce a horizon, they preserve severity without abandoning order. Black holes are not the places where the universe breaks. They are the places where the universe refuses to, and that refusal carries us to the edge of the final answer. Not why black holes are possible, not why they are dramatic, not why they are useful for astronomy. Why a lawful cosmos, once pushed hard enough, may be unable to remain itself without them. Because the moment you say that out loud, the role of black holes changes for the last time. They are no longer merely consequences. They become constraints on what a universe is allowed to be. That may sound too philosophical until you notice how physics keeps forcing the same conclusion from different directions. General relativity says that sufficiently concentrated mass energy can trap causal structure behind a horizon. Thermodynamics says horizons behave like surfaces that carry entropy. Quantum theory refuses to tolerate a world in which information can simply dissolve into nothing. Astrophysics shows that compact central engines help regulate galaxies and appear absurdly early in cosmic history. None of those fields was designed to flatter the others. They arrived with different questions, different tools, different scales, and still they keep colliding at the same place. That is not what a decorative phenomenon looks like. That is what a structural phenomenon looks like. A decorative phenomenon can be removed without forcing the rest of reality to renegotiate itself. A structural phenomenon cannot remove it, and the surrounding laws lose one of the places where their hardest consequences are absorbed, expressed, or reconciled. By now, black holes have earned that structural status. They are not just what happens after stars. They are one of the ways the universe remains internally honest when gravity, causality, entropy, and information stop being discussable in the abstract and become physically inseparable. And that is why the deepest question was never whether black holes are dangerous. Of course they are dangerous. A tidal field strong enough can pull a body apart, atom by atom. Accretion flows can heat matter into radiative violence. Relativistic jets can sterilize regions on scales that make human threat language feel provincial. But danger was always the shallowest thing about them. Stars are dangerous. Supernovae are dangerous. Space itself is dangerous if you remove enough warmth, enough pressure, enough air. Danger only tells you what something can do to bodies. Black holes matter because of what they do to categories. They dissolve the old confidence that matter is the most basic way to describe an extreme object. They erode the comfort of thinking that the inside of a system is where its deepest accounting must live. They force time, temperature, surface, information, and geometry into one framework before we know how to make that framework conceptually comfortable. They make us confront the possibility that the visible universe is only the public face of a much stricter hidden architecture. That is why black holes keep enlarging instead of shrinking as we understand them better. Usually, explanation domesticates a mystery. The subject becomes clearer, and therefore less threatening to thought. Lightning becomes electricity. Disease becomes biology. Planetary motion becomes celestial mechanics. The pattern is familiar. Deeper knowledge replaces fear with clarity. Black holes do offer clarity, but of a harsher kind. The more precisely we understand them, the less they resemble freakish interruptions, and the more they resemble exact expressions of the universe's deepest commitments. Knowledge does not make them smaller. It makes the rest of reality look more severe. That is the real psychological tension they create, not the fantasy of falling into one, not the cinematic image of a dark sphere swallowing light. The deeper unease comes from discovering that black holes are not alien to the laws we trust. They are what those laws become when no softer arrangement remains available. They are familiar physics carried to the point where familiarity can no longer protect us. And that is also why black holes are so hard to narrate honestly. If you make them into monsters, you flatten them. If you make them into puzzles, you shrink them. If you make them into metaphors, you risk distorting them. If you make them into educational content alone, you miss their force. The truth is more exacting. A black hole is one of the rare things in science that is simultaneously an astrophysical object, a thermodynamic system, an information problem, a geometric structure, a cosmic regulator, and a philosophical wound. Each description is real. None is sufficient by itself. To speak about black holes responsibly is to hold all of those layers without letting them collapse into spectacle or dissolve into abstraction. That balance matters now more than ever, because we no longer live in the era when black holes were purely theoretical burdens. We have seen their shadows. We have tracked stars orbiting invisible centers. We have watched matter heat around them. We have heard spacetime ring from their mergers. Black holes are not speculative in the way they once were. Their existence is observationally mature. What remains unsettled is not whether they are real, but what their full reality means. That distinction is easy to overlook, but it changes the tone of the whole subject. We are not waiting to discover whether the universe permits horizons. It does. We are trying to understand what else becomes true in a universe that does. And each answer so far has widened the demand instead of narrowing it. If horizons are real, then entropy has to be taken seriously there. If entropy is real there, then information has to be accounted for there. If information must be accounted for there, then our current split between geometry and quantum law is not final. If black holes also regulate galaxies, then these foundational problems are not confined to thought experiments, but embedded in the ordinary history of cosmic structure. If black holes evaporate, then the accounting cannot be deferred forever. If all of that is true at once, then black holes are not side effects of the universe. They are one of the forms in which the universe confronts itself. That is the midpoint renewed at its deepest level. Black holes are not merely things. They are tests. Not only tests of theories, but tests of whether the world can remain one world when pushed to its own edge conditions. And that reframes the phrase, the universe needs them, again, with even less room for softness. The universe does not need black holes the way a story needs drama. It needs them the way an equation needs its limiting case, the way a legal system needs its hardest precedent, the way a material needs a breaking point if it is to mean anything when called strong. Without black holes, gravity would have no fully honest public consequence for unconstrained collapse. Thermodynamics would lose one of its most severe and revealing surfaces. Quantum theory would lose one of the places where its demands become hardest to evade. Astrophysics would lose one of the engines that keeps large-scale structure from becoming simpler and less stable. Black holes are where the universe stops speaking in approximations. That line is not decorative. It is almost literal. Everyday reality is built out of negotiated conditions, moderate densities, tolerable temperatures, recoverable histories, weak field approximations, environments in which the great laws can remain separated enough for our intuition to survive. Black holes arrive when those negotiations fail. They are not the opposite of law. They are law after negotiation has ended. And once you see that, another old illusion breaks quietly in the background. The illusion that reality becomes more arbitrary as it becomes more extreme. In human affairs, extremity often means chaos. Structure fails. Exceptions proliferate. Rules bend under pressure. But in black holes, the opposite pattern emerges. As the physical situation grows more intolerable, the need for exact accounting becomes sharper. Horizons are not vague. Causal structure is not sentimental. Entropy does not negotiate. Information, if quantum theory is right, cannot simply be waved away. The black hole is severe precisely because the universe is being less arbitrary there, not more. Reality becomes hardest where our intuitions become weakest. That is why black holes do not merely humble the senses. They humble the imagination that trusted the senses too far. We evolved among moderate scales. Breathable atmospheres, planetary gravity, solid-seeming matter. Durations short enough to call permanent. Distances short enough to call far. Black holes expose how local those habits are. Matter is not always solid in the way it feels. Space is not always a neutral stage. Time is not always shared evenly. Boundaries are not always surfaces you can touch. And an object is not always best understood by asking what it is made of. Sometimes the deepest fact about a thing is what futures it forbids. That may be the cleanest way to say what a black hole really is. Not a dark ball, not a tunnel, not a devourer. A black hole is a region defined by prohibition. It forbids outward escape. It forbids ordinary reconstruction from the outside. It forbids easy coexistence between our deepest theories. It forbids the universe from pretending that unlimited collapse can remain merely a matter problem. And in that sense, it begins to look almost inevitable that the next stage of understanding will not come from treating black holes as isolated curiosities, but as keys, not keys in the sentimental sense of the answer to everything. Reality rarely grants anything that theatrical, but keys in the stricter sense, places where hidden structure becomes legible because several deep principles are forced to overlap under conditions too exacting for vagueness. Which means the next movement cannot be about more examples. It has to be about convergence. Because once black holes have done all this work, ending stars, regulating galaxies, storing entropy on horizons, destabilizing our concept of information, surviving into the far future, and exposing the cost of a lawful universe, the final task is not to add one more marvel. It is to gather the entire descent into a single, irreversible realization. Because by now, the question has become too large for any single image of a black hole to hold. Not the dark sphere, not the ring of light around a shadow, not the star collapsing inward, not the quasar blazing at a galactic center, not the silent future horizon evaporating over timescales that make civilizations look like sparks. Each image is true. Each one captures a real face of the phenomenon, but none of them, alone, explains why black holes feel less like objects we discovered, and more like conditions reality was always carrying in reserve. To gather the whole descent, you have to look at what keeps repeating. A star spends its life resisting collapse and fails. General relativity admits horizons before human beings are emotionally ready for them. The young universe begins building giant black holes embarrassingly early. Galaxies do not simply contain them, they evolve in tension with them. Thermodynamics places entropy on their boundaries. Quantum theory refuses to let them become places where information is casually erased. Rotation turns them into engines. Evaporation denies them eternity. Different scales, different languages, different disciplines. The same pressure point. That repetition is not redundancy, it is convergence. And convergence in science has a very particular kind of force. When one idea appears in one narrow context, you can still imagine it as local. When it keeps returning from independent directions, it begins to look less like an explanation we invented, and more like a feature the universe keeps insisting on. Black holes now belong to that second category. They are not merely tolerated by the cosmos. They are woven through its behavior so deeply that removing them would not simplify the story. It would leave a hole in the logic of the story itself. That is why the phrase, "the universe needs them," can finally be sharpened without romantic excess. The universe needs black holes because gravity needs a truthful endpoint. That is the first layer. Gravity gathers matter. It gathers gas into stars, stars into galaxies, galaxies into larger structures. It does not merely attract, it amplifies differences. A slightly denser region becomes more attractive, draws in more material, becomes denser still. Structure is born from this, but so is the possibility of unbounded collapse. If there were no horizon, no causal severing, no black hole endpoint, then a universe with gravity would either need some endlessly renewable series of hidden pressures to rescue matter every time, or it would have to tolerate pathological concentrations without a clean relativistic consequence. Both options feel less honest than the black hole. The horizon is terrible, but it is exact. It is gravity-refusing euphemism. The universe needs black holes because causality needs a boundary, once escape becomes physically meaningless. That is the second layer. There is a brutal dignity to the event horizon. It does not negotiate in half measures. It does not blur into poetry. It marks a clean transition in what futures exist. Outside, escape remains possible in principle. Inside, every future-directed path goes inward, however emotionally intolerable that may be. It is cleaner than a vague intermediate world where the geometry has already defeated escape, but reality refuses to say so. The horizon is not mercy, it is definition. It keeps the language of cause and consequence from dissolving when spacetime is driven to an extreme. The universe needs black holes because entropy needs somewhere to become visible in its most concentrated gravitational form. That is the third layer. Before black holes, thermodynamics seemed to belong most naturally to matter. Gases in boxes, molecules in motion, heat spread through interiors. Horizons changed that. Suddenly, entropy could no longer be treated as merely a property of volume-filling substance. A black hole says that the deepest count of hidden possibilities may be written on a boundary. That revelation is not a small technical curiosity. It is one of the great reversals in modern thought. It suggests that the universe's accounting is more austere than the senses ever implied. The black hole is where thermodynamics stops feeling domestic and begins feeling architectural. The universe needs black holes because quantum theory needs its hardest challenge to be real, not hypothetical. That is the fourth layer. If information is truly preserved, then black holes force that principle into its least comfortable form. They take the most dangerous possible case, matter crossing a horizon, evaporation threatening final loss, geometry appearing to hide what quantum law refuses to let die. And they insist that the answer must still exist. Without black holes, the tension between gravity and quantum mechanics might remain a philosophical inconvenience. With them, it becomes a physical demand. Black holes do not allow the foundations of physics to remain politely separated. They force the world to admit that our current frameworks are incomplete precisely where reality is most exacting. The universe needs black holes because galaxies need regulation, not merely accumulation. That is the fifth layer. Gravity alone does not guarantee graceful structure. It can build, but building without constraint is not the same as stable organization. Supermassive black holes, through accretion, radiation, winds, and jets, appear to help govern the rate at which galaxies cool, form stars, and evolve. This does not make them benevolent architects. Nature is not designing for beauty, but it does suggest that concentrated extremity can be part of larger coherence. A black hole can prevent broader disorder by enforcing harsher local terms. It can limit excess precisely by embodying it. And the universe needs black holes because even the hardest structures must remain inside time. That is the final layer. Black holes are not eternal loopholes. Hawking radiation, however subtle and however unresolved in its deepest informational meaning, makes them participants in cosmic history rather than exceptions to it. They persist almost beyond imagination. Then they fade. This matters because it prevents us from turning them into mythic absolutes. The black hole is not outside the universe's lawful flow. It is one of the most severe expressions of that flow. It forms, it acts, it stores, it constrains, it interrogates, and eventually it is spent. The universe does not need black holes as monuments. It needs them as phases through which its deepest rules become legible. Now, place all of that together, and something changes in the emotional meaning of the subject. Black holes stop looking like cosmic villains. Villains are intrusions. They enter a world that was fine without them and damage it. Black holes are not like that. They are not external to cosmic order. They are one of the places where cosmic order reveals its least comforting face. They are what a lawful universe looks like after every softer possibility has been used up. That is why they are frightening in a way a supernova is not. A supernova is violent. A black hole is conclusive. A black hole is the universe closing an argument. That line gathers almost everything. A star argues against gravity through fusion. Degenerate matter argues through quantum pressure. Galaxies argue against runaway cooling through feedback. Theorists argue against information loss through unitarity. Human intuition argues that reality should remain roughly proportional to experience. The black hole is where those arguments stop sounding human and start sounding final. And that is what the universe would lose without them. Not merely a class of phenomena, but a mechanism of closure. A place where collapse ends cleanly in geometry. A place where causality sharpens instead of blurs. A place where thermodynamics reveals its boundary form. A place where quantum law is forced to answer at the highest stakes. A place where cosmic structure is regulated by severe concentration rather than diffuse gentleness. A place where even extremity remains historical rather than eternal. Without black holes, reality might feel kinder. It would also feel less complete. Because the deepest lesson they teach is not that the universe is hostile. Hostility is still too human a category. The deeper lesson is that reality is willing to be exact, where we would prefer it be forgiving. It is willing to preserve law where we would prefer exception. It is willing to let consistency become frightening rather than dilute consistency to preserve comfort. That is the perception shift the whole story has been building toward. Black holes are not proof that the universe contains monsters. They are proof that the universe contains limits, and that those limits are not decorative. They are built into the way matter, space, time, entropy, and information are allowed to coexist. A black hole is what appears when those coexistences are driven to their hardest edge and still required to remain lawful. Which means the last movement cannot be about adding anything new. It can only return to the opening wound, return to the first shattered intuition, return to that phrase that sounded, at the beginning, like a statement about danger, and now feels like a statement about reality itself. There are places in this universe where outward stops meaning anything. The final task is to understand what that sentence now really says. And now it no longer sounds like a statement about motion. At the beginning, outward seemed physical, directional, almost mechanical. You heard it and pictured escape velocity, gravity wells, trajectories bending inward, light failing to climb free. All of that remains true, but it is no longer the deepest truth in the sentence. There are places in this universe where outward stops meaning anything, because there are places where the old assumptions about reality stop surviving contact with its own foundations. Outward, in the ordinary human sense, implies more than movement. It implies options. It implies the persistence of an outside. It implies that space remains a neutral arena in which paths can still be chosen, effort can still matter, and distance can still be traded for freedom. A black hole destroys that implication with terrible precision. It does not merely make escape hard. It alters the structure within which hard and possible can still be distinguished. Beyond the horizon, the issue is no longer whether one can get out. The issue is that the future itself has been narrowed into only one kind of continuation. That is why black holes feel metaphysically larger than their size. A stellar mass black hole may be only a few tens of kilometers across. Even a supermassive one, immense as it is, occupies a tiny fraction of the galaxy it helps govern, and yet their conceptual gravity exceeds their physical scale. Because a black hole is one of the rare things in nature that changes not only what happens, but what it means for something to happen. It modifies the grammar of physical possibility. It turns direction into destiny. Once you feel that, another old intuition begins to dissolve quietly in the background. The intuition that reality is built out of things first, and only then out of laws. That is how the world first presents itself to us. We meet stones, trees, bodies, fire, wind, oceans, planets, stars. We experience objects, substances, events. Laws come later, as abstractions distilled from repeated observation. It is natural, then, to imagine that the universe is fundamentally a collection of things, and that laws are descriptive habits we infer from how those things behave. Black holes reverse the emotional order of that picture. They make the laws feel prior, not because objects cease to exist, but because the object in front of us is so obviously the expression of a deeper constraint. A black hole does not feel like matter in a new costume. It feels like geometry, causality, entropy, and quantum consistency taking on a local, terrible form. It feels like law made visible. The thing is almost secondary. The rule is what stares back at you. That is part of why the usual language of fascination so often undershoots them. People call black holes mysterious. And they call them extreme. And they call them cosmic monsters. And although the phrase is crude, it is trying to point at something real. But what those phrases often miss is that black holes are not merely surprising inhabitants of the universe. They are disclosures about what the universe is when it is no longer buffered by our scale. A black hole is what reality looks like when approximation ends. That line reaches farther than astrophysics. In everyday life, approximation is everywhere. Matter seems solid, even though it is mostly field and structure. Time feels uniform, even though relativity teaches otherwise. Objects seem self-contained, even though every system leaks, exchanges, radiates, interacts. Distance seems simple, causality seems intuitive, permanence seems possible. We live inside a habitable layer of truth, not false, but softened, accurate enough for survival, stable enough for common sense. Black holes belong to the places where the softening runs out. And that is why they produce such an unusual kind of emotion. Not simple fear. Fear belongs to immediate threats. A cliff edge, a predator, a collision, even cosmic fear, in the ordinary sense, is still often about destruction. What could kill us, erase us, crush us, burn us? Black holes can do all of that. But those are still the shallowest reasons they trouble the mind. Their deeper emotional effect is something colder. the recognition that the universe is under no obligation to remain intuitively legible when taken seriously enough. That is the source of the vertigo. Not that reality is chaotic, that it is lawful in ways we were never built to find comfortable. A chaotic universe would actually be easier, in a certain dark way. Chaos relaxes explanation. It says things scatter, exceptions happen, unpredictability reigns, and the deepest answer may simply be that there is no deeper answer. But black holes do not offer that relief. They offer the opposite. They say that under enough pressure, the world becomes more exact, not less. The accounting sharpens, boundaries harden, conservation becomes more demanding, geometry becomes more consequential. The law does not fail, it becomes less forgiving. Black holes are not the places where reality goes wild. They are the places where reality goes exact. And once you absorb that, the phrase, "the universe needs them," becomes almost unbearable in its implications. Because what the universe need, in this strict sense, is not spectacle, not terror, not singular icons of destruction. What it needs is a way for its deepest commitments to survive their hardest tests. It needs a truthful endpoint for collapse. It needs a precise causal boundary. It needs a place where entropy and area meet. It needs a crisis through which quantum information can no longer remain a polite abstraction. It needs engines harsh enough to regulate galaxies. It needs final states that are still historical, still thermodynamic, still answerable to time. Black holes are all of those at once. That is why they keep outrunning metaphor. Any single metaphor collapses under the load. If you call them prisons, you miss their role as engines. If you call them engines, you miss their role as boundaries. If you call them boundaries, you miss their thermodynamic depth. If you call them thermodynamic systems, you miss their galactic force. If you call them cosmic regulators, you miss their philosophical wound. A black hole keeps escaping the frame because it sits where too many truths converge to be carried by one image. And convergence does something to the tone of the whole universe. After a certain point, black holes stop feeling like space phenomena and start feeling like revelations about existence under law. They join a very short list of things in science that permanently alter the emotional texture of reality itself. Not because they tell us the universe is magical, quite the opposite. Because they tell us the universe is coherent enough to become terrifying without becoming irrational. There is no cheap comfort in that. But there is a kind of severe beauty. Not beauty in the sentimental sense of wanting to be close to the thing. No one needs to romanticize a horizon. No one needs to pretend the abyss is warm. The beauty is colder than that. It comes from seeing that reality does not fragment when it becomes difficult. It continues. It remains itself. It keeps faith with its own structure beyond the point where our inherited intuitions would have broken. A black hole is beautiful for the same reason a difficult theorem is beautiful, or a ruthless symmetry, or a law that holds when every incentive for exception has arrived. It does not become true only under friendly conditions. It remains true under pressure. And perhaps that is the final hidden reversal in the story. At first, black holes look like negations. Negations of light, negations of escape, negations of visibility, recovery, and ordinary form. But by the time you have followed them all the way through collapse, geometry, entropy, information, galaxies, spin, and evaporation, they stop looking like pure negation. They begin to look like one of the ways the universe preserves affirmation. Not affirmation of comfort, affirmation of coherence. Affirmation that gravity means what it says, that causality means what it says, that entropy means what it says, that quantum law, whatever its final reconciliation with gravity turns out to be, must continue to mean what it says even here. Black holes are what that affirmation costs, which is why the ending cannot simply repeat that they are necessary. The word is too thin unless it has earned all of this weight. Necessary how? Necessary for what? Necessary to whom? Not to us. Black holes are not here for human meaning. The universe did not build them to teach us humility, awe, or existential discipline, though they do all three. They are necessary to the universe only in the impersonal, hardest sense. They are among the forms reality must be allowed to take if its deepest rules are to remain consistent when nothing easier can save them. That is the mature answer waiting inside the opening wound. There are places in this universe where outward stops meaning anything, because there are places where reality would rather become harsher than become false. And once you understand that, the final question is no longer what black holes are. It is what kind of cosmos is revealed by the fact that they had to exist at all. A cosmos more exact than merciful. That may be the deepest answer black holes leave behind. Not a cruel cosmos. Cruelty implies intention, not a hostile one. Hostility still imagines a universe arranged in relation to us, as if reality were capable of resentment. Black holes point to something colder and more difficult than that. They point to a world whose deepest order does not bend toward emotional legibility, a world in which consistency is preserved even when consistency produces horizons, singular limits, thermodynamic abysses, and futures from which return ceases to be a coherent phrase. That is what makes black holes feel so different from every other scientific revelation. Most discoveries add to the inventory of reality. They tell us that there is more here than we thought. More planets, more elements, more galaxies, more particles, more mechanisms beneath appearances. Black holes do that too. In a narrow sense, they add a class of object, but their deeper force is not additive. It is judicial. They do not merely expand the list of things that exist. They pass judgment on the terms under which anything can exist when gravity, time, matter, and information are driven past every ordinary regime. A black hole is not just another inhabitant of the universe. It is one of the places where the universe reveals what it will not compromise. That is why every path through the subject, if followed honestly, keeps returning to law. Not because law is abstractly beautiful, though sometimes it is. Because law is what remains when everything else has been spent. A star can spend fuel. A galaxy can spend cold gas. Matter can spend its available configurations of pressure support. Even a black hole can, over impossible ages, spend itself through Hawking radiation, but the structure that governs those changes does not retreat just because the consequences become severe. It continues to apply. And that is the final destabilization black holes produce. We are used to thinking of law as the mild background of reality, something that lets apples fall, planets orbit, chemistry proceed, light travel. Black holes reveal law in another register entirely. They reveal law as a limit case, as a hard edge, as the thing that does not become kinder when the stakes rise. They show us that the universe does not merely have rules. It has consequences for letting those rules remain true under pressure. That is what the horizon is. Not only a boundary in space, not only a no-return surface, not only a region of failed escape. It is the visible cost of consistency. There is something almost unbearable in that, because it cuts against one of the quiet myths human beings carry even into science, the belief that deeper understanding will eventually restore comfort, that if we keep going, keep refining, keep explaining, the universe will become more proportionate to the mind that studies it. The first centuries of modern science encouraged the hope. Things once thought mysterious became tractable. Chaos yielded pattern, motion yielded law, disease yielded mechanism, heat yielded statistics, light yielded electromagnetism and quantum structure. Again and again, understanding dissolved enchantment and replaced it with intelligibility. Black holes do offer intelligibility, but not comfort. That distinction matters. They can be described with extraordinary precision. Their formation can be modeled. Their signatures can be observed. Their mergers can be heard. Their thermodynamics can be derived. Their paradoxes can be sharply formulated. They are not vague. They are not occult. They are not supernatural wounds in the cosmos. They are some of the most mathematically disciplined things we know. And that is exactly why they unsettle so deeply. If black holes were chaotic anomalies, they would be easier to dismiss. We could exile them to the category of cosmic weirdness and leave the rest of reality intact. But they are not weird in that loose sense. They are lawful enough to force us to reconsider what law actually means. They are coherent enough to make coherence itself feel severe. The old comfort was this, That reality, however large, would remain roughly continuous with the scale of our experience. Black holes end that comfort. They show that common sense is not a smaller version of deep truth. It is a local truce, a useful adaptation to moderate conditions, a survival instrument. Reality at full pressure is not obligated to preserve the intuitions that work on planets, among bodies, within atmospheres, across short durations, under weak gravity. That is why black holes are not only scientific objects. They are threshold objects. They mark the point where the mind has to decide whether it wants truth more than reassurance. And almost everything about them reinforces that demand. They force us to accept that a direction can disappear from physics without anything mystical occurring, that an object can become simpler in public description while implying deeper hidden accounting, that a surface can carry more conceptual weight than a volume, that the darkest entities in nature can become some of its most powerful engines, that the ultimate endpoint of collapse is not necessarily a material state we can picture, but a change in the causal architecture of the world, that even those severe endpoints may not be final in the eternal sense, but phases in a longer thermodynamic history. Each step strips away another human convenience. The convenience that matter must remain primary. The convenience that inside and outside are always symmetrically meaningful. The convenience that information can be hidden without becoming a foundational problem. The convenience that the most extreme objects should also be the most exceptional to the overall order. Black holes deny all of that. And in denying it, they do something very rare. They make the universe feel larger not by adding distance, but by deepening necessity. The cosmos does not become bigger here because another billion galaxies were found. It becomes bigger because what must happen under certain conditions turns out to be stranger than what the senses were willing to allow. Black holes enlarge reality by enlarging the domain of the inevitable. That is why they leave such a distinctive residue behind. Not mere awe. Awe is too broad. Supernovae can produce awe. Nebulae can produce awe. The cosmic microwave background can produce awe. Black holes produce something more exact, a kind of haunting clarity, the feeling that one has not merely seen something vast, but glimpsed the terms on which vastness remains lawful. And once that clarity arrives, the whole story of black holes can be read backward. A star shining is no longer just a beautiful object in equilibrium. It is a postponement. A supernova is no longer merely an explosion. It is a failed defense. A horizon is no longer merely a dramatic boundary. It is causality becoming explicit. A quasar is no longer merely an energetic beacon. It is a black hole using surrounding matter to regulate a galaxy. The information paradox is no longer a technical quarrel. It is the demand that reality not become self-contradictory at its most exacting edge. Hawking evaporation is no longer an exotic quantum correction. It is the refusal of even the hardest structures to stand outside time. Everything reorders itself around the same center. Black holes are what the universe builds when it would rather become harsher than become inconsistent. That sentence is the mature form of the entire script. Not that black holes are powerful, not that they are mysterious, not that they are dangerous, not even merely that they are necessary. That they reveal a cosmos in which necessity itself can take a form our intuitions were never built to love. And that is why the final return must be simple. There are places in this universe where outward stops meaning anything. Now, the sentence is no longer about escape. It is about revelation. It means there are conditions under which familiar reality gives way to deeper structure without ceasing to be real. It means the world is built in such a way that horizons can form. Information can become crisis. Entropy can migrate to boundaries. Galaxies can be governed by darkness. And even the last severe objects can eventually evaporate, all without reality surrendering coherence. It means the universe does not preserve truth by staying gentle. It preserves truth by staying consistent. That is what black holes are for. They are not cosmic accidents. They are not ornamental horrors. They are not the universe breaking down into darkness. They are the places where the universe keeps faith with its own rules when every softer form has failed. And once you understand that, the fear changes. The black hole remains dark. The horizon remains final. The laws remain cold. But the cosmos itself becomes newly visible, not as a stage filled with strange objects, as an order capable of carrying its own hardest consequences all the way to the edge. And that edge is not where the story becomes abstract. It is where it becomes intimate in the most unsettling way. Because once black holes stop being those strange objects out there and start becoming revelations about what a lawful universe is willing to be, they also begin to change the meaning of everything that feels ordinary here, not by contaminating it with melodrama, by exposing what the ordinary world has been shielding us from all along. A table feels solid because the electromagnetic structure of matter makes solidity available at our scale. A day feels continuous because our lives unfold too slowly to feel relativity bite into time. A horizon, in daily life, is just a line where vision gives out and the world seems to continue beyond sight. But a black hole teaches a more severe lesson about all three. Matter is not solid in the simple way it feels. Time is not one shared river. A horizon is not merely a visual limit. Under sufficient pressure, the universe turns each of these soft human impressions into something harder, stranger, and less forgiving than the senses ever suggested. That is why black holes keep radiating significance backward into reality. They do not only tell us what happens in rare places, they tell us that the familiar world is a low-pressure version of a deeper truth. And once that realization arrives, even the most stable things begin to look provisional. A star is not permanence. It is resistance on a timer. A galaxy is not a serene island of light. It is a negotiated structure, often with an invisible concentration of extreme lawfulness at its center. Space is not an empty container waiting to be filled with matter. It is active enough to be twisted, trapped, heated, and partitioned into regions where escape itself can stop being a meaningful future. The universe is not merely made of things. It is made of conditions under which things are temporarily allowed to remain what they are. A black hole is what that allowance looks like when it expires. That may be the most difficult sentence of all, because it strips away the final comfort of imagining black holes as separate from the rest of existence. They are not separate. They are the endpoint written into the same reality that gives us stars, atoms, landscapes, and breath. They feel alien only because our lives are conducted so far from the regimes in which the deeper structure has to show itself openly, which is why the emotional residue they leave is so specific. Not despair, not simple dread, not even awe in the broad, luminous sense. Something narrower, colder, more exact. The feeling of seeing that reality is underwritten by principles strong enough to survive their own harshest consequences. That feeling is difficult to name because human culture is not built to celebrate it cleanly. We are good at revering beauty. We are good at fearing destruction. We are good at mythologizing chaos, darkness, and catastrophe. But black holes are not fundamentally beautiful in the decorative sense, nor terrifying in the merely animal sense, nor chaotic in the sense of lawlessness. Their deepest effect comes from a confrontation with coherence, a coherence so rigorous that it can produce event horizons, thermodynamic surfaces, information crises, galactic regulation, and evaporation across absurd spans of time without ceasing to be one reality. Black holes are what happen when coherence stops being comforting. And perhaps that is why they linger in the mind more stubbornly than many other scientific ideas. Other revelations can be assimilated. They can be folded into the background architecture of what an educated person knows. Black holes resist that softening, even after you understand the basic mechanisms, even after the vocabulary becomes familiar. Horizon, accretion, spin, entropy, Hawking radiation, the subject keeps refusing to become merely familiar knowledge. Because it is not only telling you something about astrophysics, it is repeatedly asking whether your picture of reality was ever deep enough to deserve comfort in the first place. That is the private pressure under the public science. A black hole does not just challenge theory, it challenges scale, it challenges metaphor, it challenges what the mind expected truth to feel like. Most of all, it challenges the old assumption that the deepest layer of reality would, in the end, feel cleaner and more humane than appearances. Black holes suggest something harder, that the deepest layer may indeed be cleaner, but in the way a blade is cleaner than flesh, or a theorem is cleaner than grief. Cleaner because it is more exact, not because it is kinder. And from that perspective, the phrase why the universe needs them reaches its final maturity. The universe needs black holes because a world with gravity cannot let unlimited collapse remain vague, because a world with causality cannot blur the point at which futures close, because a world with thermodynamics cannot ignore what happens when immense hidden complexity passes behind a boundary, because a world with quantum law cannot permit the deepest conflict over information to remain hypothetical, because a world that forms galaxies may require severe central engines to keep structure from reducing itself into simpler excess, because a world in time cannot allow even its hardest forms to become timeless idols. Each of those answers is real. Together, they become one answer. The universe needs black holes because reality must have a way to remain truthful under maximum pressure. That is the line everything has been building toward. Not truthful under ordinary conditions. Many things can appear truthful there. Approximation is generous. Weak fields are merciful. Human scales are forgiving. The real test comes when pressure rises. Collapse deepens. Information vanishes from view. Entropy demands accounting, and the ordinary language of objects begins to fail. A black hole is the place where the test is no longer theoretical. It is reality under oath. And that is why the black hole is not merely dark matter gone wrong, or starlight extinguished, or a mathematical wound in the cosmos. It is something more disciplined than any of those. It is a place where reality signs its name beneath consequences most minds would rather leave unsigned. That does not make black holes emotionally easy to live with, nor should it. Science does not owe the mind anesthesia. It owes it clarity, and clarity, in this case, is not a return to safety. It is the recognition that what once looked like a monster is, in a deeper sense, a principle. What once looked like a failure of ordinary form is actually the conservation of deeper form. What once looked like the universe turning hostile is actually the universe refusing to become false. So, when we return finally to that first fractured image, a place where outward stops meaning anything, the sentence now carries the full weight of everything behind it. It means that in this universe there are conditions under which freedom of motion yields to geometry, conditions under which hidden states outweigh visible surfaces, conditions under which destruction becomes regulation, conditions under which simplicity in appearance conceals overwhelming informational depth, conditions under which the last survivors of cosmic history still answer to time, conditions under which the laws do not retreat when the cost of consistency becomes severe. And that is the final perception shift. Black holes are not strange because they violate reality. Don't force no. Why? They are strange because they reveal how much of reality our ordinary experience never had to face. A star can glow for billions of years and still be only a postponement. A galaxy can span 100,000 light years and still negotiate with an invisible center. A horizon can be silent and still contain one of the loudest statements physics has ever encountered. An object can be defined less by what it is than by what futures it forbids. And the universe can remain lawful all the way into forms we would once have mistaken for breakdown. That is what black holes give us, finally. Not comfort, not a tidy answer, not a myth of cosmic evil. A harder gift. The knowledge that the universe is built strongly enough to carry its own harshest truths without collapsing into incoherence. And once that becomes visible, black holes no longer feel like the exception at the edge of existence. They feel like one of the places existence tells the truth most completely. Which is why, in the end, the question was never really about darkness. Darkness was only the first seduction. It gave the black hole an image the human mind could grip, a region with no light, no escape, no visible inside. But darkness is still a surface impression. It belongs to perception. The deeper story was always about what reality does when perception stops being enough. A black hole is where the universe stops translating itself into terms that evolved minds find easy. That is why it feels so final, not because it is the biggest thing, or the hottest thing, or even the most energetic thing. There are larger structures, hotter events, brighter phenomena, but almost nothing else in science compresses so many hard truths into one place with such pitiless economy. Gravity taken seriously, time taken seriously, entropy taken seriously, information taken seriously, causality taken seriously, history taken seriously. The black hole is what appears when all of them are forced to remain true at once. And that is what "the universe needs them" finally means. Not that the universe prefers them, not that it loves extremity, not that black holes are noble or sacred or cosmically privileged. Only this: a universe that allows gravity to gather matter cannot remain fully honest forever without permitting collapse to reach its lawful conclusion. A universe that allows space-time to curve cannot soften that conclusion indefinitely without lying about what curvature means. A universe that permits information, entropy, and causality to matter cannot send them into extreme conditions and then excuse itself from exact accounting. A universe that builds galaxies cannot always rely on gentler processes to regulate what gravity itself keeps trying to accelerate. A universe in time cannot allow even its hardest endpoints to escape time completely. Black holes are the form those obligations take. They are what reality builds when it refuses to save us from the implications of its own rules. That is why they do not belong in the category of monsters. Monsters are exceptions to order. They invade it. They rupture it. Black holes do something more unsettling. They emerge from order itself. They are born not from a lapse in the laws, but from the laws keeping their word too completely. They are what happens when the universe does not blink. And once you see that, something subtle changes in the emotional register of the whole cosmos. The stars no longer look merely radiant. They look conditional. Galaxies no longer look merely grand. They look negotiated. Space no longer looks merely open. It looks capable of closing. Time no longer looks like a neutral river. It looks like a structure with gradients, limits, and irreversible demands. Even matter no longer feels like the unquestioned substance of reality. It begins to look like one temporary strategy among deeper constraints. Black holes do not just add fear to the universe. They remove innocence from it. Not innocence in the childish sense. Innocence in the epistemic sense. The old assumption that if we kept peeling reality back, we would eventually reach a layer that was simpler in a way that also felt gentler. Black holes end that hope with extraordinary discipline. They reveal a deeper layer. Yes, they reveal astonishing clarity, but the clarity is cold. The deeper layer is not gentler than appearances, it is stricter. And that is why the final residue is not panic. Panic is for immediate danger. This is something slower. A kind of altered sight. The sense that reality, beneath all its visible warmth and structure, is held together by principles that remain themselves, even where our intuitions would rather they didn't. The sense that the universe does not preserve coherence by staying within the range of the imaginable. It preserves coherence by remaining lawful beyond the point where imagination keeps pace. Black holes are the proof of that. They are proof that the universe can become harsher without becoming irrational, that it can become more severe without becoming arbitrary, that it can generate horizons, paradoxes, engines, and evaporating abysses without ever ceasing to be one world governed by one deep insistence on consistency. That is why they stay with us. Not because we expect to meet one, not because they threaten daily life, but because once they are understood, even partially, they alter the background meaning of everything else. They teach you that the visible world is not the whole world, not merely because there are hidden things in it, but because the laws beneath it are prepared to become far less intuitive than the surface ever warned you. There are places in this universe where outward stops meaning anything. Now, at the end, that sentence has become larger than black holes. It means there are conditions under which reality stops offering the comforts our minds mistake for fundamentals. It means there are thresholds beyond which escape, recovery, softness, and ordinary description no longer survive. It means there are places where the universe would rather become terrible than become false. And that is why it needs black holes. Because without them, gravity would be blunted by mercy it never promised. Causality would be denied one of its hardest edges. Entropy would lose one of its most profound surfaces. Quantum theory would be spared a crisis it has to answer. Galaxies would lose one of the severe mechanisms by which structure is kept from burning too quickly through itself. The cosmos would feel kinder, but it would also feel less true. Black holes are the price of a universe that does not dilute its deepest laws when those laws become unbearable. They are the cost of coherence. And perhaps that is the most unsettling realization of all. Not that somewhere out there are regions from which light cannot escape, but that such regions are not anomalies. They are part of what it means for reality to remain reality under maximum strain. They are not mistakes written into the cosmos, they are signatures. The universe keeps them because, in the end, it cannot keep faith with gravity, time, entropy, information, and structure without them. So, the black hole remains what it always was. Silent, dark, final-looking, but now it means something different. Not the death of law. Its most uncompromising expression